So let's summarize all the line integrals and surface integrals. First, let's start with the notation. Notation for scalar line integral is, we're saying scalar, therefore you're expecting a scalar function, and then ds. For the arc length, basically. And in this case, f can be a function of two variables or a function of three variables, right? In calculus 3. And so this one is a scalar function. Then you have vector line integral, which you're expecting a vector function. So vector field f dot dr, and here is a vector function, vector valued function, scalar valued functions. Now the notation for a scalar surface integral is, again, what I'm forgetting, over a parameterized curve, Here it becomes surface, so over a surface, and you will have again an f, this time a function of three variables, and d capital S, double integral for, and this is your, so that was the arc element. This is the surface element. And then you will have a vector surface integral. See here we had scalar and scalar function. And now vector surface integral looks like this. F dot ds with a capital S. And of course, when we're saying arc length element and surface element, then what happens to these with the vector on top of them? They become the vector arc element for dr and the vector surface element for ds with a vector on top. Now, these are nice notation and remind you of what we're supposed to be doing, but that's not exactly what we use when we're trying to take the integral. How do I do this? With the scalar line integral, you evaluate. So you parameterize C, basically both of these two. You have to parameterize C with R of t, and then nt between A and B. And then basically this notation becomes the integral of f parameterized at R of t from A to B, magnitude of R prime of t, R prime dt. So this part is the ds part, basically. Now, what do I do with the vector line integral? Again, the parameterization is the same, except that we don't have the scalar valued function, we have the vector valued function. And then instead of the, because it's supposed to be a dot product, or this is how I memorize it. I say, well, there should be a dot product, so I have to have a vector, and therefore, instead of the magnitude, I'm putting in R prime of t itself and dt. So this dot product becomes the a scalar that you integrate. Integral then becomes an integral in Calc 1. Now, how do I do surface integral when it's scalar? this time around, you have to parameterize the surface S by a G of U and V, and then U and V, they are within the region D. So again, you notice that over there I said A and B, here I said region D, because let's say if the region is a circle, then I cannot give you two numbers for upper and lower bound of U and two numbers for upper and lower bound of V. So if it's non-rectangular region, then you want to write it as D. Sometimes you put the U and V down there, so you remember that D belongs to U and V. So the surface integral becomes surface integral over du and V, dA U and V. Why? Because I'm parameterizing F at G of U and V. And then you want to multiply that by magnitude of N. So magnitude of N, what is N? N is basically, in general, it doesn't matter if I put plus or minus in here, but it's plus or minus G sub U. Sorry, I forgot that. Cross G sub V. Depending on, and it doesn't matter for scalar surface integral, but it matters for vector surface integral, because over there the magnitude just gets rid of whether or not it's plus or minus. So again, you use F, you parameterize F on G of U and V, then you multiply it by the magnitude of N, and then you take the integral over the bounds, double integral over the bounds of U and V. It becomes a double integral. It becomes, here it becomes a 15.2 or 15.4 or 15.6, I guess, those chapter 15 integrals. These are the sections. And now the last piece is this one, and that is the double integral. Again, U and V. Now parameterize the vector function F at G of U and V, and then dot N of U and V, dA U and V. So this is either du or dv or dv, I'm sorry, du dv or dv du. And so other things to notice again, here N matters, depends on, so you either use the G sub U cross G sub V or the negative of that, depending on what direction of flux you're trying to compute, basically. This one you have to decide about the sign, because you know that basically the normal vectors are either you can find normal vectors in two different directions. Now, the next thing that it's asking is if there is any other properties, that any other formulas that you can use. And so the other formula is not, there are some other formulas you can use. One would be with, let's say for F dot dr, sometimes people use either, if it's two-dimensional, then they use, they say that F is equal to P and Q, or F is equal to P and Q and R, depends if it's two-dimensional or three-dimensional, and then they write it as P dx plus Q dy over C. Okay. And then The other thing that sometimes people use is the other, obviously there are multiple notations for this, but another notation for this one is basically f dot n ds over s. So another notation for the surface integral is this. That means that you just, instead of dotting f evaluated at g by capital N, you dot it with a lowercase n, and then you take the scalar surface integral. And this is a preferred method if you already know what n is. N, the normal vector. And so this can be preferred method, but then you have to do a scalar surface integral after you do the dot product. So basically, if you just use the parameterization n, it will automatically go through the process that takes you to a regular double integral. Here you do dot n, then you have a surface integral that is scalar, and then you go to the vector surface integral. So all of that said, what are the physical properties? Let's move it a little this way. And so for the scalar line integral, so physical, basically applications. Physical applications. Scalar line integral gives you scalar line int gives you you can either use the define the mass by having the mass density. So if you have the mass density, if F is the mass density or whatever density, you get the total mass, like total mass of a wire or you can get the total surface area of a wall. Or total amount of wall you have in there if you don't want to use surface area, so it won't be confused with the other one. The vector line integral gives you the work done by the vector field. The scalar surface integral, scalar gives you the total mass of the surface, or whatever you density function you have, total of that basically on the surface of the surface. And the last one gives you